So as Sean said, my name is Inakim Choi. I'm with ACOM. We are the consultant at the Turnpike, Florida Turnpike Enterprise. This is not a project specific. It was a research paper. So it's not something that we were recommending implementing. It's an experiment on the freeway to test how the autonomous vehicles are going to have an impact on the capacity. I'm sure most of you read a lot of the CAVs because it's a hot topic in our industry right now. And for the last few years, the hype has been, becoming more realistic than how it was probably 5 years ago. Because 5 years ago, if you ask someone about the direction of CAVs, people are saying like at 2020. Now we are in 2022, but people back in 2015, they were projecting that we're going to have approximately probably 50% of CAVs on highways. And now we are 2022, we still don't see that much. They are still they are there, but we are it's not to the point that was projected before. So my presentation, the overview is we're going to go through the background, and we have some motivation because this was a research paper, as I said, and the objectives for why are we doing this, and the simulation approach that we used. And we're going to see look at the simulation runs and results, and we're going to have some closing comments. So the highway capacity manual recently just released the capacity adjustment factors based on the penetration rates, but the assumptions are not really clear because most of the research and the research that led into the development of those adjustment factors, it was just changing the headway. And that's not how the CAVs are going to work. For us to go to have the full benefit of the CAVs is part of the infrastructure being reconstructed to accept the technology, and the CAVs, they have capability to execute advanced strategies more than what the highway capacity manual was assuming, just to change the headway. So this is the graphic that I usually very interested in looking at. Most of the time when I read about the CAVs technology on papers or the reports, it's from US DOT. So you can see here, it's all combined aspect of the transportation technology that's going to bring us to the full benefit of the CAVs. So on the outside part of these three circles, you see you have intelligent transportation systems, which we already have for a long time. And on the other side, the automated vehicles, right? And we have connected vehicle systems. So when you talk to people, sometimes there's confusion between the automated vehicles and connected vehicles. An automated vehicle can be just a robot running through the highway, not necessarily being connected. And the connected vehicle might just have capability to connect and communicate with other vehicles and the infrastructure, not necessarily have the capabilities to identify completely the infrastructure by itself, right? You have to have a driver, and the driver receives the message through the probably onboard units, and then execute whatever they want to do that. But for CAVs and all the intelligent transportation systems that are in the infrastructure, the intersection of that's where we're going to really harness the full benefit of the CAVs and the technology that is we usually talking, so we have project going on at the bigger scale at Turnpike, and some of them we are working with our travel demand forecasting models, and on top of that we are extracting the subnetworks and running this. So our approach is and assumption is that we're going to have the gradual adoption of CAVs within the near term. And our second assumption is that the higher income households, just as other technologies, people with money are going to be the first people to adopt the technology at high rates. And we're going to see the capacity and reliability increase, and the facilities that are going to be mostly favored, are the limited access facilities, which are freeways. And on top of that, which with simulation we don't usually do a lot, but for macro level travel demand forecasting, we do that, is that we're going to have the induced trips. We're going to have, cars without people inside. So they're going to increase their trip and the VMT is going to go up. In the region that I'm working on the research is we have other project going on at higher level. I mean at a bigger scale, and we are looking at the macro and micro analysis zones. Like for what you see on the top level, there is the regional penetration rate, and the maps those shows the penetration rate at micro analysis level as a function of the penetration rate at regional level. So we found out that based on the assumption and the data we have, the zones with higher income, where people with high income are coming from, those are the zones that you're gonna see the concentration of the CAV adoption. And this is from one of the papers from one of the colleagues that we work together. It was presented. Probably some people here who attend TRB, they might be familiar with this graphic. So at micro simulation level, what motivated us to do this is that there are some experiments that were done, and physically using the small proportion of equipped vehicles, and those vehicles are controlling and harmonizing the stream flow. So you can use a small proportion of equipped vehicles, like very advanced technology, to influence how vehicles behave on the stream. Even some vehicles are not equipped. And simulation with the CAV in which traffic flow conditions were controlled following kinematic wave theories, like absorbing the shock wave using the technology. And they said the research that shockwave and jam absorbing strategies using Platoons were applied, and you can control the flow using the just small proportion of vehicles within the stream, not necessary to have the very high penetration rate. So the objective of this experiment is several times when we have big projects like PDNs, we go to public hearing, people ask you, why are you proposing widening? Why we are expecting to have CAVs that are going to increase the capacity. So the answer for us, we didn't have clear answer because we don't know. We are projecting 20, 25 years to come. And when people ask you that, you don't really have an answer, because no one at this point has a clear picture where we're going to reach 100% of CAVs in the future. The impact at each penetration rate has really been quantified, but when the time horizon is not really explained like with confidence. So what we did is what's going to happen when we have a small proportion of CAVs in the highway, and those CAVs they can be, we can install like roadside units, and some of the vehicles that they just have connectivity technology, they can be receiving information from the roadside units, and then form the platoons and harmonize the speed within the freeway. So that's what we try to do in this paper. So the experiment we did on the Turnpike, Florida Turnpike, if you've been to Florida, probably you might not be to South Florida, especially. In other parts of Florida, probably you can use that facility, but in South Florida, mainly, you might not be able to avoid using the Turnpike if you're traveling especially from Orlando to all the way to Miami. So the Florida Turnpike is the one that you see the pink. That's the Florida Turnpike owned facility, and the other facility on the section that you see that is running east-west there, that's the Sawgrass Expressway. It's part of this the Turnpike as well. So our experiment was from just south of the Sample Road interchange to north of Sawgrass Expressway interchange. Within the this segment, this is the most congested segment within the Broward County in Florida. So we run other experiment to alleviate the congestion for near term, but this one was just for the experiment, and we were to send to the publications. So the approach we used because the experiments we started before VSIM 2020 was released, and then which has other, ways to implement the CAV, like very advanced strategies. We used VSIM 11, and the base model was calibrated using the FDOT guidelines, and our algorithm was to control CAVs and form platoons. We wrote it in C++ using the external driver model API. So this is not the pseudocode. We simplified the algorithm explanation for, it was on purpose, because sometimes you submit a paper, not everybody has a computing background, so you have to explain in a way that someone who is reviewing your paper can understand better. So we had 4 modules. The first one was the vehicle information module, that the vehicle send information, and the second module was the communication mode, that the CAVs can communicate, and we had a platoon information module within the code, and the last one was the platoon update, looking at the platoon if the vehicles are left and the information is sent to other vehicles, and other vehicles are willing to join the platoon. That module will update the platoon size. So and all of this, it's not like we came up with the idea like invention. We tried to look at the script that come with the VSIM installation. Some of them, like, they already have a way to implement that. Some of them are in Python, but we were able to translate into C++. And so there was 2 script that it translated from Python to C++. There's one that is called car to X, car to everything, Python script. We use that, and there's a platoon formation code. It's also in Python, and we took that and translated into C++. I'm not going to go through the. I think the presentation is going to be available, and you can go in detail for that. So we ran 3 simulation models, and because we wanted to see the near term, 2030, we didn't want to run for 2045 or 2035. We just wanted to see in near term, if we implement this without widening, without doing anything on the highway, what's going to happen in the capacity. So we ran the simulation with 0% penetration rate of CAVs and 5% and 10%. And then we measured maximum throughput at 4 different locations and take the average. So once we extracted the results, we were actually able to see that was an improvement in the capacity when you have at least 5% of CAV penetration rate. So these are the plots. I'm not going to have much of the take much of your time. You can see the base calibrated maximum throughput was at 1950. That was the maximum before the breakdown on those stretches on the highway. And the reason we have data and we have the maximum capacity you can go in Florida, which is considered to be acceptable when you're running the experiment, the simulation. So we were able to hit 1950. So with 5% CAV penetration rate, we were able to get higher 490 vehicles per hour per lane, higher maximum throughput compared to 0% CAV penetration rate. And at 10, we were able to hit 850 more vehicles per hour per lane compared to 0% penetration rate. So, as I said, this was just, it's not something that we are recommending to implement. We were just running the experiment to see what would be the effect of the penetration at low rate. And if we execute like those, the strategies that the connected vehicles can execute, not just to changing. When you look at the result, actually, you can see that we are not trying to manipulate the headway. The proof for that is the jump density. You can see whether it's a CAV or the just the conventional vehicles, we were able to break. The breakdown was almost at the same jump density. So, but if you look at the papers that they are trying to change the headway, you'll see the one with the CAVs has a very extended jump density, which is not really realistic, because whether it's a CAV or conventional vehicles, there's physical constraint of the infrastructure that you cannot extend beyond certain values. So the closing comment is that there are opportunities if there are technology that can make other vehicles that are not that advanced to receive the information and join the platoons, not to cause too much lane changing within the segment, which is going to alleviate the shock wave. And our experiment showed that the formation of platoons actually is more it has more effect on the on capacity improvement than just the headway changes. And I just wanted to point out the limitation that there are other physical constraints that might hinder achieving this demonstrated maximum throughput. We might, if we implement in the physical in the site, we might not get these values that we showed in the experiment, because we might not be able to account for everything that is within the infrastructure. And we didn't include the ramp terminals, which are for the freeway main contributor of the bottlenecks. So if we include those, we might not be able to hit those values that we shared here today. So with that, open for questions, and that's my contact information if you need any detail or you have any more questions to follow up.